screen. I'm sharing it.
Yes, sir.
You're able to see my screen?
Yeah, sir. Yeah, sir.
Yeah, so there is an error that is popping up since quite some time. I don't know
Okay.
why. Okay, fine. Yeah. Okay. So let me blow this up. Okay, so most of you are aware of what MEMS device is all about. So now we'll look into what pressure sensor is. A pressure sensing device is quite uh, 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 it's a very known device to many of us, and the name itself says it's a pressure sensing device. So there are two types of pressure sensors. One is the piezoresistive type, and one is a capacitive type of a pressure sensor. Here we look into piezoresistive type of pressure sensor. This is a quite interesting one because most of you are aware of the fundamental concept of Wheatstone network. Whether we come from whatever background, whether we are mechanical engineers or instrumentation, all of us, if we are a science student, yes, we have studied what is Wheatstone network. Okay, it comes from the same principle. Okay, and where we use the piezoresistive type of pressure sensor is what we will see. Okay, and where another type of pressure sensing device is the capacitive type, which is rarely used for only for very high pressure applications. We will see that as well. Okay. Okay, so with piezoresistive type, since it's an electromechanical device, so naturally it has electrical component and also the mechanical component. So first we will see what all the mechanical optimizations are involved in this one. Okay, and then the electrical optimization we'll look into it. So first we will see what is the desired specification. So in the desired specifications, we will have a tabular column. So any design, when we want to do it, we will put a tabular column. This is the working condition of the device. So that's what we start with. In this case, it's an absolute pressure sensor. Okay, absolute pressure sensor meaning I'll explain this what is absolute and differential pressure sensor in the later slides, showing you the model itself. Okay, so for now, please take this as absolute pressure sensor device, and its operating range is 10 bar. Okay, 10 bar. So it 0.1 megapascal is equal to 1 bar. That's the conversion. Okay, so this is 50 bar, and we have a proof pressure 1.5 times the operating range. So that's the condition to be set, and burst pressure should be greater than 5 times the operating range, and the nonlinearity should be 0.5% full scale. Sensitivity 10 millivolts per bar. Okay, and hysteresis, okay, 0.3% of full scale operation, and base resistance of 2 kilo ohms, and temperature range of minus 45 degrees to 70 degree. So someone has given us this requirement. Okay, and now we need to work to achieve a pressure sensing device of which meets these requirements. How do we start? So as this assignment, how do I do it? Is what we'll see what are all the things that are involved. So we'll be developing a piezoresistive type of pressure sensing device, and pressure sensor design and fabrication we will see, and then the signal conditioning and electronics, and the pressure sensing pressure transducer system and packaging components and testing. Okay, so first we will see the flow chart of it. Okay, so when we look into the flow chart, the user specification starts here from the top. Okay, Dr. Prasanna, is my voice and also the slide, is it in sync or is there a delay?
No, is it fixing, sir? No problem. And raise the volume
Okay,
from
fine.
yourself, sir. Lightly raise.
Okay, fine.
Okay.
I'll raise the volume. Okay, so fine. So we have a user specification. when we have a user specification, sorry, I think yeah. So then we see the sensor chip design. So sensor chip design, whether it is with ROIC design or PCB layout, first we will see that. Okay, or else a mask has to be prepared or what. So if the mask data preparation is mask data preparation as per the process design rules of manufacturing, we will see that. And then further we will look into the sensor wafer fabrication at foundry. Okay, and then we fabricate the wafer level device. So all these devices are fabricated in bulk, just like our famous sweet of Karnataka, that is Mysore Pak, where we have the molten sweet put on a tray, and then we cut into small pieces as it cools down, and small cakes are available. Okay, so just like that, we have multiple devices that gets fabricated, and then it is cut into small pieces based on the unit number of devices. So that's why the cost of the device comes down if the volume increases. Okay, fine. If it is meeting the requirement, then a die is attached to a packaging device. Okay, packaging and further wire bonding will go through. If the wafer level characterization fails, then reject the faulty dies. So if we are planning, say, about 10,000 devices in one wafer, typically the yield will be somewhere around 65 to 70%. If we achieve 65 to 70%, it's very great. Okay. So here we reject those devices which do not meet the requirement. So we reject faulty devices. Okay. So that's how the flow chart runs through. So at every condition, we have some test protocols, and then we test them and take the ones which are working. So finally, when testing for TC and programming, if it is performing very good, then we go forward, or else it will be thrown out there also. Okay. Yeah. So further bonding processes will, after the fabrication, bonding and packaging and other things will carry forward. So at every stage, the testing is done, and then we select those devices which meets the requirement. Okay, so now let's look into what is Wheatstone network. Wheatstone network, all of you are aware of what is Wheatstone network. It is a four resistor device connected in series parallel combination, R1 parallel to R3, R2 parallel R4. Okay, so we have a Wheatstone network. So here also we take these resistors in the Wheatstone network form. So what are these resistors? These resistors are basically piezo-resistive material. How are they achieved? We'll see that. So Wheatstone network contains four P-type pressure sensors, and piezoresistors are realized by selective doping. So selective doping. So selective doping can be done here. I'll show you in the software how the doping is done. Okay. And under no pressure condition, what is the Wheatstone network, whether it is in balanced condition or unbalanced condition, we can test them. When pressure is applied on the top surface of the diaphragm, it undergoes deflection, inducing stress at the edge of the diaphragm. So this is the catch here. So it undergoes a deflection, inducing stress at the edge of the diaphragm. Okay. So now we have a square plate on the center, on the top side of the surface. When we apply pressure, the maximum displacement happens in the center. Okay. Naturally, those areas which are fixed, we will experience stress. Okay, so here it undergoes stress because of the deflection. Okay, and Wheatstone bridge becomes an unbalanced due to change in resistance, and that's how pressure induces strain. Okay, and this change in resistance will reflect in change in voltage. Okay, the same working principle of a Wheatstone network. But the question remains is, where should we mount these resistors? That's the question. Okay, so here, when we look into the design optimization of mechanical aspects, So here we have four things. One is size of the pressure transducer, input pressure range, overpressure range, and burst pressure range. Okay. So here, how do we select the size of the transducer? We will see that. Okay. So there are few criteria to be met to achieve the mechanical design aspect for a MEMS pressure sensor device. So if a pressure sensing device has a thickness of say 10 micrometer or a 50 micrometers, I will keep it as 100 micrometer. Okay. So here that the first criteria says that the design of the pressure sensor involves, sorry, I think I'll go to the criteria next. Okay. Okay. So we'll see the analytical aspects of it. Okay. The design of the pressure sensor involves optimization of thickness in both X, Y, and Z directions. Okay. It's a square membrane and the maximum deflection can happen based on the pressure that is applied. So what is the safe zone of pressure that is applied? We will see. Okay. The maximum burst pressure is an important criteria for choosing the thickness of the diaphragm. The stress in the square diaphragm is maximum at the edges uh, and is given by the relation sigma maximum. Okay. So we'll see the criterias now. So criteria one. The criteria one says the maximum deflection of the membrane should be less than 1/5 of its thickness. Okay. Any pressure sensor, if the thickness of the thin film or the membrane is 100 micrometer, to be operating in the safe zone condition, its deflection should be less than 1/5 of it. If it is 100 micrometer, then the deflection should not cross beyond 20 micrometer. That is the first condition. Okay. So here, based on this one, what we do, the D max, so maximum displacement. So here you can see the E is the Young's modulus, nu is the Poisson's ratio, length and thickness. So what we do, we calculate based on multiple values and then decide what should be its thickness. Okay. So criteria one is this. So for the tabular column, which I showed you in the beginning, for this to be achieved, the desired specifications to be achieved. So we, based on these analytical conditions, we can set the size of the device to be 720 micrometer by 720 micrometer, and the thickness of the membrane is 30 micrometer with pressure of 50 bar at full scale. Okay. So when 30 micrometer of thickness is achieved, then the Dmax, it's less than 5 times of it. Okay. So the maximum displacement that comes is 5.33 micrometer. This is less than 1/5 of the diaphragm thickness. Okay. Hence it satisfies the condition one, that is the criteria one. Okay. So now we'll look into criteria two, the proof pressure condition. That is the criteria two. The ratio of maximum deflection at proof pressure to the diaphragm thickness should be less than 0.5. The things which are there in the square bracket are the references which is there in the last slide. So these numbers in the square bracket are references. Okay. Yeah. So now if this is the case, for this, with a diaphragm of this dimension, 720 micrometer by 720 micrometer and 30 micrometer thickness, the maximum proof pressure condition is 75 bar. Okay. So 75 bar, but we are not applying 75 bar at all. Our plan is to go only up to 50 bar. So it satisfies criteria two also. The third one is the burst pressure condition. The stress induced at the burst pressure should be less than the yield strength of single crystal silicon. So we are using single crystal silicon, meaning silicon 100. Okay. So here the dimensions, which are 720 by 720 into 30 micrometer, results in generating a stress which is less than 7 gigapascal, okay, of the stress. Okay, so the yield strength of silicon is much higher than that. So the absolute burst pressure is 3 to 5 times the operating range. So it meets the third criteria as well. So here this dimension does not go, or the stress induced on this one due to the pressure that we apply of 50 bar, the stress does not cross or come near to the yield strength of the single crystal silicon. So it meets all the three criteria. Okay. So here, and we also check what is the natural frequency of the device. So based on all of these things, we calculate the D max, and the D max, what we get is 0.107 micrometers. Okay. Yeah, so this is the membrane settling time. Okay, so when we apply pressure, naturally it requires some time to respond, and once we release them to come back to its original position, so there is a settling time. Okay, so that was the mechanical optimization of the device. Now let's look into the electrical optimization. So here, electrical optimization meaning that the 4 resistors that we are using. So I'll come to this slide later. I'll show you here. Okay. So here, okay. So this is what the piezoresistive type of pressure sensor looks like from the top view. Okay. So what we have, R1 is called as the longitudinal resistor, and R2 and R4 are called transverse resistors. R1 and R3 are called longitudinal resistors. Okay, why we call them in those names, I'll come back to this. Okay, so now we are talking of the electrical optimization. So we see the electrical optimization in terms of change in resistance. So change in resistance is given by this one, delta R, with respect to the intrinsic resistance, or resistance at which there is no input load. Okay, so we have sigma 1, sigma L and sigma T, that is the longitudinal and transverse stress, which are again dependent on the pi coefficients of the device. Okay, so we have the pi coefficients, pi 11, pi 14 and pi 44. Okay, sorry, pi 11, pi 12 and pi 44 for the for N type and P type. So here we are inducing boron. So naturally it's a P type injection that we are trying to do. So we take these piezoresistive coefficient values. Okay. Now, if the device, okay, yeah, so now the stress distribution. So this is called as the longitudinal resistor. Okay, when it is on the sides, because why we call this as a longitudinal thing, so a longitudinal resistor, because you see in the second image where you see a rings. Okay, when we apply pressure either from the bottom or from the top on a square diaphragm like this, maximum stress is distributed, or the stress is displacement happens this way, and the maximum stress is seen at the edges which are fixed. Okay, so naturally we have a longitudinal resistor pulled in X and Y, I mean top and bottom side, the width of the resistors are pulled, okay, due to the expansion of the device. Here, when we look into the transverse thing, so we have the pull on the transverse direction. So here we have the pressure or the stress that is experienced in transverse condition and another in longitudinal condition. So hence it is called transverse stress and longitudinal stress. Okay, so here the name of those resistors are also called as longitudinal resistors and transverse resistors. Okay, so here when we apply the pressure, okay, so there's a change in resistance. So the electrical optimization can also be done by finding out the resistivity of the piezoresistive material based on the depth. Okay, based on the depth of doping that we have done. Okay, first what we do, we apply what we do is we run the simulation without applying any pressure. Okay, and then by applying voltage we will see what is the current that is induced. From that we can calculate what is the resistance value. Okay, so now we will apply pressure on that. Naturally there is a imbalance condition for which there is a change in voltage, for which there is an induced current, so for which there is a change in resistance that can be calculated. All through this, all through the simulation that we can do. Okay, so here the resistivity is calculated in terms of atoms per centimeter cube. Okay, so we have based on the doping concentration we can calculate them. So these are some of the analytical aspects of the doping. Okay, so if the doping concentration is 2 exponential 17, then the electrical conductivity will be 1.4 10 power 9. Okay, Siemens. So here we have the resistance in terms of kilo ohms. And similarly, when the doping concentration changes, there is a change in electrical conductivity and also there is a change in resistance. So here, based on the doping concentration, we can see the change in resistance happening. So this is the packaged version of the device. What we have the DIP or packaging or quad flat package. So 16 pin or 8 pin. So based on the standards of the packaging, IC packaging format, so we package the device. So here I'll show you how this is being done. Okay, so meantime, if you have any questions, I can wait for about 2 minutes and then I can open up the software. Okay, so do you have any questions until now?
Yeah, please unmute yourself. You can ask the question before going to the step-by-step procedure in the software. Yes. Okay, sir, you can continue.
Okay, fine. Yeah, so here the GUI what you are seeing is the okay, so what you are seeing now is the installed version of the software where different modules are available for different applications. Okay, so here we have different types of approaches. One is the top-down approach, one is the bottom-up approach, which we discussed yesterday. So we'll look into what is bottom-up approach. Since the fabrication is it's a little difficult to understand how the fabrication process flow happens, let me stress upon that. So I'll use the bottom-up approach method for the design. Okay, so here let me open this module called IntelliFab. IntelliFab is a module where we do a lot of fabrication simulation. Okay, so this is where we can or any process engineer can use this tool to optimize his process if he's doing it on a clean room. Okay, so what we do is we have database of different substrates: copper, glass, indium phosphide, quartz, silicon, silicon carbide. Okay, we have different deposition materials, we have lithography. Okay, and then we have etching aspects of the fabrication. So at every stage, based on the design criteria that we want to do, we define this step. So what we do is define the dimension or define the substrate first, and above that there is a material called PR, photoresistive material. Above that we have UV, that is a lithography simulation, and then we do the doping, boron implant, okay, B-ion implant, and then we do the etching of it, and we have the deposition Si3N4 silicon nitride, and then a PR material is kept on that, again UV lithography, etching of silicon nitride material. So if you carefully observe, the CMOS process is nothing but deposition of different materials, and lithography is done based on the mask pattern, and then etching is done on the material which we have deposited. The etching pattern is based on the mask pattern. Okay, so we'll look into this one now. So here we look at the visuals of that, how this gets fabricated. Okay, so it is not just a graphical representation of different materials and different colors, it is a fabrication simulation. Okay, so those things which are difficult to be achieved can be optimized by doing the fabrication simulation. Okay, so it's trying to open FabSim. Let's wait. Yeah, it's open. Okay, so we have the die size. So how does this die look like? So this is what the die look like. So what we do initially, we create a layout first. Okay, we create a layout in a module called blueprint. Okay, in blueprint, based on the type of processes that we have, different layers are created. So the name DRI stands for deep reactive ion etching, and metallization, and piezoresistive material, and via contacts. Okay, what are these things? I will show it to you. Okay, one by one. So here, this is what it looks like. The layout tool goes like this. So I'll just show you the layer fill. Okay, so the blue ones are the resistors, and the yellow entity or the yellow color one is the wire. So blue ones are the resistors, yellow ones are the wires. Okay, it is connected by the wire. Resistors are connected by the wire. You can see there is a small gap between the two portion. It is not connected here. Okay, so this is where the measuring part comes up. Okay, we'll see this gap, or the advantage of retaining this gap at the analysis part of it. Okay, I'll close this. Okay, I don't save. Now I click on next. So we have a PR material deposited, and we are trying to dope the boron ion, B ion implant. Okay, and we keep the mask, and then we do boron ion implant. See, you can see here each step is shown here, boron implant. So the boron implant goes like this. Okay, I'll show you. When we do doping, it goes into the material. Okay, it is not on the surface of the material, it is inside the material. So based on the doping concentration and the depth of doping, you can plan to have the resistivity value. Okay, so here we get this. Okay, so I'll model with, okay, yeah, boron implant. So now you can see on the surface, it is not on the geometry, it is inside the layer. Okay, it is not on the geometry or on the surface, it is inside embedded. Okay, so this is what the doping is all about. Okay, it is injecting the impurity, or that's what we know. Okay, and then we deposit Si3N4 to isolate the resistors from the metal. Okay, so we create a via contact. So we create a small hole. I'll again show you with a cross-sectional view. We create a small hole there. You can see that the pink entity is isolated from the top entity here. Okay, the purple is is making the isolation. So Si3 and 4 is an insulating material. Okay, that's what we have deposited. So you can see that we remove only that part of it. So it is like the wire bond is this. Okay, so this is what we are trying to do, is the via contact. Okay, so here we create a small opening and then we put a metal on that. Okay, so the resistors are connected via the metal. So we deposit the entire metal and then let me show you that. The via contacts, you can see the metal. So here this side is cut because it is cross-sectional view is different. Okay, so we have a piezo resistor device like this. So I'll show you the top view of it. Okay, so these resistors, the pink entity, are embedded. The white ones are the metals. And how are they connected? Via the wire. So we'll see that here. Okay, so these are connected via the wire. Let me pull back so that it gets more clear. Okay, so at every point I can do the cross-sectional view and see how my device looks like. Okay, so this is a tool where you can even teach the fabrication methods very easily. Okay, you can do nano fabrication also. Okay, for IC gates and other things. Okay, so once this is set, we keep a mask below it. Deposition of a mask, because here if you look at the presentation file, here the device looks like this. The device at the bottom has a hole and we see a cavity here. That is what we are trying to create now. Okay, we open the mask and then we remove some parts of silicon there. So removing any crystalline material is called as bulk micromachining. So that's what we are trying to do. So bulk micromachining generally takes some time on a laptops. Okay, so it's more advised to be used on a desktop machine. Okay, so let's wait for about a minute. Yeah, it's done here. So let's look into the cross-sectional view. Okay, then I hide them. So you can see that a cavity is set. So why this cavity is there? Because the pressure is applied from the bottom side. Okay, and there is a deflection on the top side. Okay, so that's why there is a cavity at the bottom. So you can see that cavity position is also exactly matching the resistors. Okay, we cannot have the cavity as we like. Okay, it has to be defined appropriately. Okay, so once the fabrication simulation is done, we push this design to analysis. Okay, so here probably, okay, so I think if I okay, so I'll close this and then I'll open. Once we do the design of it, and then we push this design for analysis, and we open this design in a module called thermoelectromechanical module. Okay. Okay. So at this point, with fabrication as such, do you have any questions? Anyone has any questions? Okay. I do not hear any questions, so I'll go ahead.
Sir?
Okay. Yes.
At the beginning, you showed a gap for the measurement, right?
Yes.
At the end, we couldn't see it. So, is that?
Oh, that one? Ah, yeah, that's right. Okay, I'll show you that. Probably I shouldn't have closed this FAPS and it's taking time now. Yeah, so here the gap is there. Even the gap is seen here. I'll show you on the device here also. The gap is seen. Probably I'll use this tool.
Okay.
Can you see the gap?
Yeah. Yes, sir. Thank you.
Yeah. Okay. So this is at the device level. If you want to see the same thing on at the fabrication level, you can go to the last step. Yeah, I'll pause this here. I'll not do bulk micro machining. So here, when I want to look at the gap, I think gap is still not made available. I think exposure is high. Gaps should be somewhere on the other side. Okay, so I think graphically it is not shown somewhere on the 4 sides.
It's okay, sir. No problem.
Yeah. Okay. I'll go ahead. Okay. So at the device level, we have this gap here. Okay. We have pushed this design here, and then we do a static simulation. Let's do a static simulation here by defining this as a piezoresistive material. Okay. And then we apply different material properties to this one, to different materials. So the one which I click is the one which I select. I click on import material. I select the material of my choice. Here in this case, it is silicon 100. Okay, I click OK. Since I've already set, I'm click on to the cancel. Okay, we have the Si3N4, which is this insulating material. And then we have the wires, which is turning red here. Okay, and we have the piezoresistors. So here you need to see what are all the properties that we are trying to apply. So if we are doing an electromechanical simulation, electromechanical can be capacitive, electromechanical can be piezoresistive also, electromechanical can be piezoelectric also. So based on the functionality of the device, we will see what are all the properties that are important. Ultimately, the properties are thermal properties, electrical properties, and mechanical properties. So, okay. So here, specific heat, thermal conductivity hardly matters. Okay. We are not worried about that much as we worry about the density and elastic parameters or stress and strain gradients and piezoresistive coefficients. Okay, So here we don't worry about thermal properties much. We don't worry about the magnetostrictive properties. We don't worry about piezoelectric coefficients. So based on what is the type of sensor, the and functionality of that sensor, we look into the properties of those materials only. Okay. Here there is a catch. The catch is these are piezoresistors. Okay. Here material 3 is wire, and we still define it to be piezoresistive coefficients with pi value as 0. Okay. And if we are trying to give 0, then what is the use of giving it all? Instead, I would rather say none. Okay. But still we have given it as a table with pi coefficient 0 because we do mechanical simulation and electrical simulation separately. Okay. Okay, let me run that simulation and then explain that to you because that will take some time. Okay. So here we apply pressure on the top surface. On the top surface, we apply pressure of what? 0.1 megapascal. That is 1 bar of pressure. We apply and we fix the boundary conditions. Fix the boundaries means those planes which are fixed, tightly held. So we say these are the regions which are tightly held. Okay. And then we do the mesh. I'll keep this coarse mesh as it is because it runs the simulation faster. So let me run the simulation as it runs. Okay. I was also telling you that we have applied piezoresistive coefficients to wire also, but we have maintained it as 0. The reason we have done that is because when we do the electrical simulation, we take only the electrical part of the device. Which is the electrical part of the device? It is resistors and wire. Okay, we don't take the whole device again. Now, if I want to do the resistor in the software, it will not take those entities or those elements which are not defined as piezoresistors. Okay, what should I do now? Then if I don't define the wire to be a piezoresistor with a pi coefficient 0, then for my electrical simulation, the software takes only the resistors. Okay, if it takes only the resistors which are not connected by the wire, what should I do with 4 resistors which are not connected by wire? So hence I will fool the software that's saying that this wire is also a piezoresistor, but the pi coefficients are 0. Okay, so that's what I'm trying to do. So now the simulation is run and then we see the displacement. So the displacement is seen maximum at the center. Okay, so for 0.1 megapascal of pressure, we have 0.014 of micrometers of displacement. If you want to see the animation of it, you can see the animation. This is how it runs through. Okay, so you can see that there is a small deflection. Probably I will have to enhance that. I'll stop that video. I will enhance it by 50 times. So here, probably if we apply more pressure, we can see the deflection happening. Okay, so here you can see that there is a deflection that is happening. Okay, so I'll stop the video, stop the animation, and then we will see this is the displacement maximum. So what I also said is we will see the stress variance. So stress variance is called von Mises stress is what we will see. The stress distribution is happening maximum at the resistor's position. Okay, so here you can see that the maximum stress is happening there. So the longitudinal and transverse stress is there. So what we generally do is, say we have decided the resistivity value, we have decided the dimensions, everything we have decided, but we don't know where to mount the piezo resistors. We know the direction where to mount it, but where we have to mount exactly in the square geometry, if that is the case, then what we generally do is we create the device without the resistors, without the wires, and then we apply the pressure. We will see those regions which are showing maximum stress. In those regions, we mount the resistors. Okay, so that's the criteria that we follow. Okay, so here you can see that the maximum stress that it is seen is 7.68, okay, megapascal of pressure, which is much less than the yield strength of silicon. Now I have the value of stress and the displacement for the pressure that I've applied. Now I want to do the electrical simulation. Okay, so now I click on extract resistor mesh. Now I have extracted resistors. So in case if I would have not defined the wire to be a piezo resistors with pi coefficient 0, then only resistors, the pink entity, would have come. So with only pink entity which are not connected by wire, what should I do keeping those things? So hence we are fooling the software to get the wire also. Okay, what we do here in mechanical simulation, we applied pressure, we saw the displacement, and we saw the stress distribution. Here we will see the electrical simulation. So simulation settings, we don't do anything, materials is already applied. I go to loads, I go to load and then select phase, and in this region I apply 5 volts. Okay, and at this, oh, okay, I think its response is very slow on my PC. Oops, sorry, I think I'll have to close some programs. My PC is unable to handle it. Let me open the example again. The module crashed actually. Okay, so give me a minute. I'll just run the simulation again. To get the electrical aspect, so I'll have to run the mechanical simulation also. Okay. Yeah, so while this runs, if anyone has any questions till now, I think I'll be able to answer.
Please.
Sir, in real time also, will it take this much time, or it will be more faster than this?
Real time meaning?
I mean, fabrication of these piezoelectric sensors.
No, piezoresistive sensors depends on where you fabricate it. Okay, if you are fabricating it in an industry, it goes in one go. One process is set and another process is set in a serial manner. But when you do it in academic foundries, it will take extremely long time because they work on slot basis. Okay, so it depends on your number of masks that you have and a type of material and the dimensions that you have. So based on that, the cycle time, the process time is set. So generally, as an industry, if I look at, if all the designs are optimized, then if the foundry wants to start working on it from the beginning to the packaging, easily it will take about 2 to 3 months.
Oh, okay. Thank you, sir.
Yeah, Okay, so I'll generate the stress distribution. Yeah, and then go to mesh, extract resistor mesh. Okay, I've come back to this. So I go to phase, and one side on the phase, I apply 0 volts. On this side, I apply 5 volts. Okay, so remember, I am applying 5 volts on this side, and diagonally opposite, I am applying 0 volts. So in a Wheatstone network, we know the 2 points where we apply the voltage, and we know the 2 points where we measure the voltage. Okay, so now if these 2 diagonal points we are applying the voltage, naturally these 2 diagonal points we measure the output voltage. Okay, so now we apply the voltage, and then we set the temperature of the resistors. We'll tell that all the resistors are in room temperature only. I will mesh the design. So say 50. I think 50 is too coarse. Put it as 10. Okay, so now mesh is done, temperature is set. I'll run the simulation again. So now it is doing the electrical simulation. So I've applied voltage, and the resistors are set to 25 degrees of temperature. Yeah, so the simulation is done now. Now, if I want to see the potential generated, I can see the potential. So I have applied 5 volts here. I have applied 0 volts there on this corner. So now I want to see what is the voltage that is applied. So now I click here at this point. It shows 2.49. You can see at the bottom. Okay, there is a message 2.49. So I'm expanding it 2.49 volts. At this point, I want to see the voltage. It is 0 volts. So the potential difference is 2.49. Okay, now what I do, I will redo the simulation again with 0.2 megapascal of pressure. If I do the simulation with 0.2 megapascal of pressure, then I will get one more value of voltage drop. So I will have two voltage drop values. So I take the difference of it and then calculate the sensitivity. So I will say the value that is achieved now is V1, the with 0.1 megapascal of pressure. And if I get V2 value for 0.2 megapascal of pressure, then I will put V2 minus V1 divided by P2 minus P1. P2 is 0.2 megapascal, P1 is 0.1 megapascal of pressure. So I take the difference of it and then calculate the sensitivity of my device. Okay, so this is how a piezo-resistive pressure sensor should be designed. Okay, so and simulated well. Okay, so now here there are few case studies that can be made. So I have given you one work done example which has already been fabricated, tested, and which is achieved. But as such, to achieve this design, what are all the things that we went through is what I can show you. Okay, so here we have to meet the design criteria first. So I'll summarize first and then show you. another module called as parametric designer, how it will help us. Okay, so here first we met all the mechanical aspect criterias, and then we electrical aspect criterias, and then we modeled the device. So as researchers, if I want to understand if the doping concentration increases, what can happen? Okay, another is in case if the deposition of the depth of doping increases, then the thickness of my piezoresistors also increases, what can happen? Okay, so there are structural changes that can be planned to understand the functionality of the device much better. Okay, so each one of them can be parameterized in such a way that the complete clarity of the device can be taken. Okay, so for that, let me open one more module called parametric designer. Okay, so so until now, any questions? Until now, any questions?
Okay, sir, you can continue, no problem.
Okay, so I just paused my screen. I'll just open up this module and then share the screen again. Okay, so here there is one piezoresistive material. So I'll be sharing my screen now again. So we had one of the case study that one of the research student was trying to do is this. So he wanted to understand how the dimension works for different for the variations of dimension, how the device responds is what he wanted to study. So here what we tried to analyze is we created different layers. Okay, so the layer goes like this. I'll not show you this, I'll show you the layer order. So Si1, Si2, Si3, boron implant. So one by one, I'll switch on and then show you. Okay, so we had this cavity. Above that, we had the membrane. Above that, we had one more thin layer of the same material. And then we had the boron implant. And then we had the wires. And we had the via contacts. And then we had the metallization. Okay, so here, if this has to be parameterized, okay, what should I do now? So if this has to be parameterized, then I have the case like this. So I open up this module called parametric designer. Okay, so parametric designer. So in parametric designer, we have different file elements. Okay, to port MEMS elements, drag and drop of these elements. So here standard structures can also be made, but we are not trying to make using these elements because this device as such, the piezoresistive pressure sensor, cannot be made with element based modeling. Okay, it has to be a 3D CAD model. So what we do, we take up a blank file. So in this blank file, we will tell that this file is nothing but it is this layout. Okay, so we create this. Okay, and then we will feed the value. So what we do is we go to global, sorry, not this. We go to layer parameters and then start adding different layers, SI1, SI2, SI3. How did I choose these names? These names exactly match my SI1, SI2, SI3. Okay, I'm trying to link the two files here. Okay, so what is SI1? SI1 is okay. So here we have so we have the structural where it is not parameterized. From 1 to 10 there is only one dimension. So here this is how we read it. From 1 micrometer to 10 micrometer, are there any steps? No. If it is 1, it is no. Okay, and next step, so from position 20 we have up to 10, from 20 micrometer, sorry, from 10 micrometer to 20 micrometer, that is thickness, but there is only one step from that. So here you can see that we have 6 steps. So we set the value between the two. This is the membrane thickness. If the membrane thickness increases, how the pressure changes is what we are trying to see. So all the layers we set as 1, 1, 1. There are no number of steps here. Only one layer is parameterized. Okay, only one layer is parameterized. Okay, and then we click OK to that, and then we go to control center. Okay, in control center we will tell the software, so for the parameters that we have set, please generate different layouts. It will generate the layout, and we please mesh the design. It will mesh the design, and I click start. I do the mesh design of it. So the meshing is done. So I go to loads and boundary condition. So it will open the design for me in thermoelectromechanical module. I've already set the dimensions for it. I hope it is all set. No, it is not. So I go to simulation settings. I will tell it's piezo-resistive material. And then materials. I'll not change any other material other than the resistors. Okay. So piezo-resistive material. Okay. 6.6 E minus 3. I'm just giving some arbitrary value. Okay. And then the wire, sorry, I think wire is okay. So we are just doing the mechanical aspects. Pressure, we go to pressure, phase on the top. We apply, say, 1 E minus 3. And then we go to boundary. We fix the boundaries. At the bottom side, we fix them. Okay, and then we save this design. I click save and then exit from that module. Now I click start. So all the boundary conditions and other things are set, and then I click solve. 64-bit. My PC has some 5 GB RAM, so I can set it as 4000 and click start. So now when I click start, so 6 variants of thickness, the software will simulate 0.1 kilopascal. 1 E minus 3 megapascal is what the unit input that is given. So it is 1 kilopascal. So 1 kilopascal of pressure is applied on the device whose thickness keeps changing 6 times between 19.5 to 20.5. Okay, so what will be the what will be the displacement that is seen? Okay, that's the result that we are trying to do. Manually, if the same thing is being done on the by recreating different design with different thicknesses, then it's extremely a time consuming activity. So for that, we can use this module called parametric designer. Okay, so it has to do it for 6 times. So I assume it is doing the 4th time now. Okay, it is running the simulation for the 4th time, from the 4th design. I think this is the last one. Yeah, so it's all done. So I click and go to results. So here you can see that I can extract layout parameter 1, so I think oh, this is a 3D graph. Okay. Oh, I think it's failing to generate the plot. No. Oh, I think there's some issue here. Okay, so I'm sorry, I cannot show you the graph as of now. Okay, so on the right side, what we get is the parameter value for different thicknesses. What will be the displacement for different thicknesses of the parameter? So here we parameterize 6 times. So it has done the job for 6 different thicknesses. So the graph gets plotted on the right side. So for some reason, I think the graph is not being plotted. Okay. Okay. So here, what I'm trying to tell you is we need not parameterize only the membrane alone. So we can parameterize both in X and Y directions, the width, the length of it, and the piezoresistive material dimensions, both in X, Y, and Z, can be parameterized. So when we get maximum data for the working condition on the working condition of the device, then we can plan to tune any type of device. So we get the complete hold of the device by parameterizing different dimensions of the device which are there in different layers. Okay. Yeah, so this is how you can optimize them. So here at this point, I'll take a pause. In case if you have any questions, we can discuss. And further, I'll show you the element-based modeling and then close the session.
Some
So
questions
do you
is
have
there,
any
sir?
questions?
Yeah, sir. Is it the balanced bridge? How it to simulate variable register? You can go to chat box and some questions is there, sir.
Okay, I'll open up the chat box. I'll stop sharing my screen. Are there any questions in the chat box?
Yeah, sir. Is it the balanced bridge? how to simulate variable resistor.
Okay, how to, oh, okay, fine. So that's a good question. So here you can plan to change the resistivity value here. If you want to change variable resistance, you can vary the resistors here itself based on the temperature conditions. Okay, so it's a balanced condition where it is a variable resistors. Okay.
How current is measured because there is a gap.
How current is measured?
Because there is a gap.
Okay. Here as such, okay. So we'll see the current, the active current. So this is a part of the device. Okay, 1 second. Let me apply, sorry, not applied current. Current density, normal. Yeah, so we get the current density value. So this sensor, if it has to, a current has to be measured on this one. This is the distribution of current is what we get. But when you want to do it as a measurement, in simulation, this is what you do. But in the real time, this is a part of your circuit, the complete circuit. So there you can measure the current by probing onto the at the respective point. Okay, so you can probe with respect to the ground here at the zero potential value, or you can plan to have a wire from the wire bond here, and then you can measure the
You are
current.
sharing the screen, sir?
Oh, sorry. Oh, okay, I forgot. Is my screen visible now?
Yeah.
Okay, so here, okay, I repeat one more time. The current density can be measured here. Okay, so you can see the current density distribution across the device. Okay, in simulation, this is possible, but when you want to do it in the practical application, when do you want to measure the current? So this device becomes a part of your circuit, and that's when you can measure the current. Okay. Are there any more questions?
Yeah, sir. One more question is there. These
Okay.
designed only for to design and manufacture piezo sensor like MEMS, useful in any other application areas.
Using this software.
Yeah, sir.
Yeah, I mean, this tool is designed specifically for designing and designing MEMS devices. That's the agenda of the tool. And other than that, you have other aspects. MEMS is one part of it. Other things are like signal conditioning system, which are essential for MEMS devices that can be simulated, designed and simulated well, which I'll show you in the next module. And another is the fabrication methods. So while the multi-physics, the device functionality is simulated on the FEM principle, finite element method or boundary element method, the nano fabrication or the micro fabrication, which is a CMOS process, can also be simulated here. Okay, so while this MEMS adopts CMOS, but CMOS fabrication is much bigger. Bigger than the MEMS process itself. So the same CMOS process is used even for IC industry also. So you can plan to even do the simulation of your CMOS devices like inverters and NAND AND gate and other things. This fabrication process simulation can be simulated also.
Hello. How to
Yes.
obtain the license for VTU colleges?
For
VTU colleges.
VTO colleges?
How to obtain the license?
Oh, okay. Fine. So if that is the case, then I have a file which I assume that I have the permission to share because someone shared this with me from one of the VTU college. Okay, so yeah, so maybe in another minute or so I'll share that. Okay, probably at the end of
Session. Okay, sir. Okay. Sir, one
end
more
of the
question.
session, probably I'll share that. Okay, so for VTU colleges, you have that facility.
Sir, one
Okay,
more
so I'll
question.
go back to yes, sir.
Any open source tools for smart sensor design?
As of now, in my purview, there are no open source tools available for smart sensor design as such, but there are few softwares available. One is IntelliSuite, another is COMSOL. There is one more tool called SugarMems. There are other tool called MEMS Pro. Yeah, so these are some tools which are available in the market for MEMS application. Okay. Yeah. So any more questions?
You can continue, sir. At the end, we can ask you questions.
Fine. Sure. Yeah. Okay. So here we have this module called Simple. Okay. A MEMS device is like is a sensor. So what I would say is we have 5 different sense organs in our body. Okay. So is this 5, 6? 5 or 6?
5, sir,
So 5
probably.
different, yeah. Okay. So 5 different sense organs in our body. So now the taste or the smell or what we hear or the sense of touch that we get are are sensed only if the brain works very well. Okay, so if the brain does not work very well, then there is no use of these sense organs at all. Okay, so similarly, MEMS device actuators, design, sensors, everything is good only if it has a very good interfacing circuit. Okay, so building an interfacing circuit is extremely a challenging task for MEMS devices. So for that, we have different modules available. So while we have this module called Simple for top-down approach. Okay, so we also have these digital elements and electrical elements where we can connect electrical circuits for MEMS devices. Okay, so here we have, you can see that. So these are MEMS elements. I delete. So we have capacitors, we have transistors. Okay, so okay, all active and passive components. We have gates, we have flip-flops. So all these signal conditioning, all these signals which are carried from the MEMS devices have to be read very well, and it has to be processed very well, and it has to be given in the form of a readable output. So for that, the brain activity is more important. So we need to understand the signals that are coming from these sensors. So for that, a good interfacing circuit called as ROIC, readout integrated circuit, is essential. So a readout integrated circuits are important, and you can interface them here within the software itself. And then for further a gate level simulation or interfacing this with a nano circuit, to interface this with nano circuits, which you can do it on Synopsys or Cadence tool, you can push this to a VHDL file. So you can take this file to a compatible Mentor graphics simulation tool, and then you can interface there. Because Mentor graphics as such is built for some applications wherein you cannot do MEMS simulation there. The advanced features which are available in Mentor graphics are not available in IntelliSuite. So you please try to use both of them to complete the MEMS enabled system. Okay, so while MEMS device is very innovative to do it, very innovative and a challenging task to do it, but if it is not interfaced properly with the electronic circuit, then the sensor, whatever we have created, is of no use, because it is sensing and it is giving some good result, but the fellow who is reading the signals are reading it wrong, then we cannot help in any way. Okay, a building and interfacing circuit is very much important. Okay, so here this module can help building an interfacing circuit. And another thing that I want to stress upon is the ambient conditions. So the ambient condition meaning the environment where we operate this device should be with some ambient parameters. Okay, if it is in a high pressure value, the high pressure environmental area, then the performance can come down. If the temperature is very high, then the performance can change. The viscosity of the fluid around it, the fluid meaning it can be compressible or incompressible. So viscosity of that, the mean free path of those molecules, so and the film coefficient of it. So all these ambient conditions are also important for the device to be operating in a good condition. Okay, so with this I would like to conclude this session. In case if you have any further questions, we can discuss. And I wanted to show you these information where you for where to get the software available for VTU colleges. So recently, one of the user shared this photograph with me. Probably you might have seen the same photograph because it's your internal university letter. Okay, so I will just share the screen. I will just hide the institute name who shared this one with me. Okay. I think, yeah, I think it's a very generic letter. Yeah, so I'm sharing the screen now. So hope you can read the letter. So it is from, it's a letter from 3rd September. So this letter has been shared to many VTU colleges, and this engagement between the company and the VTU has happened much before, much 10 years before. And probably what I remember from office discussion, it should be in 2006. Okay. Okay, so this provision is available for you to get the software from VTU directly at substantial reduced cost. Okay, so this is what I heard. This is the letter. If you have not seen it, this is the letter which is a recent one, which is shared from VTU directly. Okay, so you can directly contact VTU to get the software from them. Yes. Okay. I'll open the chat box.
Circuits.
Okay, so what about fabrication of simulated MEMS circuits? Okay, Yeah, so fabrication, there are a few academic fabs which are available in India. Hope you are aware of those fab labs. SENSE, Center for Nanoscience and Engineering in IISc, and there are few INUP programs from IIT Bombay, and probably INUP program is stopped now. I think funding is no longer available. That's what I heard. Those education institute have the fabs, so you can contact them. But as such, we have also taken up fabrication. We do it outside India, and then we have also delivered few fabricated devices also. Okay, so those who are interested can go to IAC, and those who want to see their devices working, we get it done outside India also. Okay, so you can contact us for more details.
So participants are unmute themselves and ask the question. For researcher also to how to buy and ask the questions. Yes. Okay. Now over to Shobha madam. One second, one question is
Yeah,
there.
any standard textbooks available? Yes, there are no standard textbooks available unless your university prescribes it. But there are few basic MEMS books which are available. MEMS handbook by Mark Madu is one, and Professor KJ Vinoy at IISc, and Professor GK Anand Suresh from Mechanical Engineering IISc, and Professor VK Atre from ECE Department IISc, and Professor Gopal Krishna from Aerospace Engineering. Four of them have written a book for VTU itself on MEMS devices. I think that's available for you in market. And I also see one more book from one of the co-author called Professor Anil Nandi at BVB College of Engineering. He has also he has one book which he has co-authored with some Chinese professor.
Okay, sir.
Okay.
Yeah.
Thank you, sir.
Okay.
Thank you, sir. Actually, yesterday you had introduced us with IntelliSuite software and also helped us to explore how it can be used to optimize the device within a short duration and how it can be interfaced with the other EDA tools such as Cadence, Mentor, Graphics, and Spice models. Thank you, sir.
Okay. Yeah. Thank you.
Hello.
Yes. Yes, sir.
Yeah. Thank you, sir.
Yeah.
And,
thank you very much.
From yesterday, you have taken a lot of pain and you explained all the what IntelliSuite software, how we can design particular piezoelectric sensor, especially in the piezoelectric sensors. You've taken us into step-by-step mode, how we can initialize the values and how we can select the elements, etc., etc. And for the nowadays, I think MEMS is very hot topics. You explored as to how to design and how to involve that in your research, in our research work. Thanks for exploring into IntelliSoftware and software, sir. Thanks. On behalf of electrical engineering, I heartful thank you. I hope that one will continue the same work with us. Thank you, sir. Thanks.
Yeah. Okay. Thanks. Thanks, everyone. Those who wish to get more details, you can write to india@intellisense.com for any specific
YRM,
details
sir?
on the software.
YRM, sir?
HPK.
Yes, sir.
We should thank all you actually for getting such an very excellent person for the session. Okay,
Yes, sir.
and we have got very good information. And be in touch with such people, such professors, so that it will be useful for our institution and department and institution.
Yeah, thank you, sir. Thank you, sir. Thank you, sir.
Okay.
Thank you, sir. Sripada sir,
Okay.
sir?
Yes,
Sir?
yes,
Sir.
Prasanna, sir.
We'll
Tell
hope
me.
you'll continue the same relationship because we
Thank
have
you very
the
much.
PG
Yes.
in control and instrumentations. Probably in next few days, I'm going to meet you personally. We'll see that
Okay.
one, sir.
Sure.
Thanks for
Certainly,
your
sir.
cooperation, sir. Thank you, sir.
Okay. Thank you. Thank you very much.
Okay.
Thanks, everyone, for patient listening. Hope we'll continue the association later through IntelliSense software. We'll catch up based on users' requirement. Okay. Thank you. Thank you. Bye-bye.
Thank you, sir. So, Chandrasekhara Chogali, sir, you want to say something? Hello? Unmute yourself,
Yeah.
sir.
So, okay. Yeah, I'm available. So, in case if you have anything, you can tell me.
Okay, sir. Okay, sir. Okay.
Thank you.
Sir, please, Chandrasekhara College, sir, please unmute yourself.
Sir, unmute yourself and.
Hello. Hello.
No, thank you, sir. Nothing to tell, but tell the video should be started.
Pardon, sir. Pardon. I didn't get.
Volume is very low.
Very low,
Sir,
sir.
your
Please.
volume is too low.
Okay. No any issues, sir.
Okay, sir.
Thank you.
Thank you, sir. Thank you.
Okay. Thank you very much.
Okay. Thank you.
Thank you. Bye.
Okay.
Yeah.
Thank you, sir. I'll contact you later, sir. Okay. Thank you.
Okay. Sure, sir. Thank you very much.
Sure,
Bye.
sir. Thank you. Okay. KPS, madam, we'll end the meeting.
Yes, sir. Okay.
We'll end the meeting. Maheshan, we'll end the
Mahesh,
meeting.
feedback form?
Mahesh? Yeah, feedback we already posted.
Okay.
Maheshan? Professor Maheshan?
Maheshan is smiling. What's the reason?
Yes. For
We can
photo.
end the meeting.
Photo ಓದ್ಬೇಕಲ್ಲಪ್ಪ.
Yes, sir. Wait. Participants, please wait. Esteemed participants, please come to video. We'll take one more snap. Please come to video. Please come to video for 1 minute.
Please start video.
Please start video. Thanks to all. Please come to video.
Because in the when the session started, Maheshan was not there. Right, Mahesh?
Okay. Yeah, thanks.
Network issues. Sir, okay, sir, come to the video.
Yeah, I already there. I taking snaps. You take also screen.
Hello. Please don't forget me, sir. I will be come video tomorrow, sir, morning. Before
Definitely, sir.
Definitely.
And one more thing from my side. Wait, Maheshan.
I have taken.
For all participants, even though in the morning you are unable to control because I don't know what happened in the morning. After applying the control application and the sensor application, it's going to correct itself. Thanks for your patience from past 4 days. We'll have one more day and we'll hope same patience from your side. Thanks one and all. We'll meet tomorrow at 9:55. Thanks. Thank you. Thanks. You can leave the meeting, sir and madam. Okay. ಏನಪ್ಪ ಪ್ರೊಫೆಸರ್ ಕೆಪಿಜಿ
Unmute ಮಾಡ್ಕೊಳಕ್ಕೆ. Unmute.
ಮಹೇಶ ಏನ ಮಾತಾಡ್ಬೇಕಾರ ಸರಿಯಾಗಿ ಬೇರೆ ಸಿಗ್ನಲ್ ಬೇರೆ ಸಿಗಲ್ಲ ಸೈಡ್ ನೋಡು ಫೋಟೋದ ಬೇರೆ ಹೊಟ್ಟೋಗ್ತೀಯ
ಬ್ಯಾಂಡ್ ವಿಡ್ತ್ ಲೋ ಇರೋದ್ರಿಂದ ಅವರಿಗೆ ಬೇರೆ ವಿಡಿಯೋಸ್ ಬರಲ್ಲ.
ಕೆಪಿಜಿ
ನಮ್ ವಿಡಿಯೋ ಬರ್ತಾ ಇದೆಯಪ್ಪ? ನಮ್ ವಿಡಿಯೋ ಬರ್ತಾ ಇದೆಯಾ ನಮ್ದು?
ಬರ್ತಾ ಇದೆ. ಆಯ್ತು.
ಓಕೆ ಥ್ಯಾಂಕ್ ಯು.
ನಿಂದೆ ಫಸ್ಟ್ ಹಾಕದ.
ಹೇಗಿದ್ದೀರಾ ಈಗ? ಹೌ ಆರ್ ಯು ನೌ?
ತುಂಬಾ ಚೆನ್ನಾಗಿದ್ದೀವಿ.
ಓಕೆ. ವಿಲ್ ಪವರ್.
ಹೌದು.
ಬೇಕಲ್ಲ 6 ಜನಕ್ಕೆ ಗೈಡ್ ಮಾಡಕ್ ಬೇಕಲ್ಲ ವಿಲ್ ಪವರ್.
Okay, we'll end the meeting. Yes.
Okay. Thanks.
Okay, thank you.
Mahesh.
Mahesh is not here. We'll end the meeting. Okay.
Okay, fine.